So the next and last speaker of the morning session is Franz Ciceri, and he's going to talk about towards holography for the IKKT matrix model.
Yeah, so hi everyone. First of all, let me thank the organizer for this nice conference and for giving me the opportunity to present my recent work in collaboration with Henning Zamtleben about this IKKT matrix model. So this model, as the name suggests, is a series of n by n matrices, SUN matrices in 0 space-time dimensions with 16 supersymmetries and SO10 invariants. So the action is given by the following formula, and involves 10 bosonic matrices, which I call X here. So the index A runs from 1 to 10, which transforms in the vectorial representation of SO10, and 16 fermionic matrices psi, which transforms in the spinorial representation of SO10. So here I don't write explicitly the spinor index on the matrices. And so this model was originally proposed a long time ago by Ishibashi, Kawai, Kitazawa, and Tsuchiya as a non-perturbative definition of type 2b string theory. And of course, this begs the question of how space-time and gravity can hide and emerge from a series of pure matrices. So in this talk, I would like to take a modern perspective on the question, which relies on the fact that this matrix model actually arises in the context of holographic dualities. And the holographic dualities that are relevant here are the ones that relate strings or supergravity series on the near-Horizon geometry of DP branes, which is of the form of an ADS spacetime in p+2 dimension and a sphere factor in 8 - p dimension. And so this side is related to p+1 dimensional super Young-Mills series with 16 supercharges. So of course, for p is equal to 3, this is the very well-known ADS-CFT correspondence between type 2b strings on ADS5 cos S5 and an equal 4 super Young-Mills in 4 dimensions. So as you decrease p, the field theory on the boundary of that lives on the boundary of the ADS space becomes more and more minimalistic, but it's still conjecture to encode the full string theory on the gravity side. So when you reach the extremal case of p is equal to -1, the field theory living on this 0-dimensional boundary of this 1-dimensional ADS space is actually the IKKT matrix model, and so this suggests a duality for this IKKT matrix model. So despite intriguing and highly non-trivial result in this IKKT model, this duality has remained so far largely unexplored, and I think that this is partially due to the fact that there hasn't been any clear dictionary that has been established between fields in the bulk and operators in the matrix model. And that means also that there has never been really operators that have been identified that can be computed and compared on both sides. So in this talk, I would like to make a very humble step in this direction and argue that the lowest BPS multiplet of single trace operator in the IKKT matrix model is realized in the bulk as the lowest Kaluza-Klein fluctuation around the 9th sphere of the near-Horizon geometry of D-1 brane, and that this lowest Kaluza-Klein fluctuation can be consistently described at the nonlinear level by a one-dimensional supergravity theory. Okay, so if this all sounds kind of mysterious to you right now, it's pretty good because the goal of the talk is to make it more clear. So essentially the plan is to start with the gravity side, and only at the very end I will come back to the matrix model. So the machinery we have that we use on the gravity side is, the notion of a consistent Kaluza-Klein truncation. So let me start by saying some words about this. Oh no. It doesn't appear okay, there are some parts of text that don't appear. But okay, you have another PDF viewer or sometimes. I'll try. Everybody close their fingers. Okay, so maybe I can continue in the meantime. So what we'll be interested in is, yeah, this is okay. And then, no, okay, it doesn't work, but okay, I'll do it without it. So the relevant Kaluza-Klein truncation for us here are Kaluza-Klein truncation of gravity theories on spheres. So it means that what you do is you start from some gravity theory and you expand all your fields on a background, which is a sphere. If you do that, you get an infinite number of Kaluza-Klein mode. And when you do truncation, it means that you keep only the lowest Kaluza-Klein mode in this tower. And in particular here, the ones that I want to do are called this Pauli truncation, where these lowest modes include a spin 2, as well as some non-abelian gauge boson for the SOQ plus 1 isometric group of the sphere, and a bunch of scalar fields as well. And so the dynamics of this lowest mode is described by a lower dimensional theory, which is a gravity theory coupled to SOQ plus 1 Young-Mills, and some scalar fields that come with a scalar potential. So the question is whether you can do this truncation consistently, in the sense that the modes that you have kept are not going to source the mode that you have thrown away. It is actually a non-trivial question for the sphere. When you do it on the torus, it's simple because you keep the zero mode on the torus, and because they are all singlet under the isometric group of the torus, you know that they will never be able to source non-singlet. But in this case, the modes you keep are not singlet under this SOQ plus 1. I mean, the Young-Mills fields are in the adjoint and the scalar fields are charged. So the consistency of the truncation is not ensured. So in practice, what you actually have to do is that you have to write a truncation ansatz for your high dimensional field, where essentially for each higher dimensional field, you write it in terms of the lower dimensional field, and the dependence on the sphere coordinate is captured by some kind of geometric quantity like the embedding coordinates of the sphere, or the Killing vectors, or the Killing tensors. And then you have to plug this ansatz into the higher dimensional field equation, and you have to show that the whole coordinate depends on the sphere factorizes out and leaves you with the field equation of the lower dimensional theory. Of course, this is usually very hard to do because these truncations at Z are very nonlinear, and gravity theories are very nonlinear to start with, so it's difficult to prove. And in fact, what we know is that this does not work for pure gravity. If you start for pure gravity in D dimension, you cannot do such sphere truncations. And so the only way for these sphere truncations to work is if you start from some matter-coupled gravity theories with specific matter content and specific couplings. And it turns out that the cases when it works, I mean, these are typically the couplings that appear in supergravity. So here I'll just consider one very famous example of a consistent sphere truncation. So it was shown in 2015 by Baguet, Home, and Zampleben using modern techniques relying on exceptional field theory, that you can actually truncate type 2b supergravity on the phi sphere, and that it leads to a maximally supersymmetric supergravity theory in 5 dimensions, which has an SO6 gauge symmetric group. So 15 vector fields and a lot of scalars which are charged under this SO6 symmetry. So why is this an important tool? It means that, okay, it's hard to construct these sphere truncations, but if you have them, by definition, it allows you to uplift any solution of the lower dimensional theory to a solution of the higher dimensional theory. So if you scan the scalar potential of this lower dimensional theory and you find a critical point, then with your truncation ansatz, you can immediately uplift it to a solution of type 2b supergravity. If you find a different solution, well, you also be able to uplift it. Of course, the internal space will have a different geometry, but the topology will be the same. Okay, in particular, in this theory, there is a critical point at the center of the moduli space, which is an ADS5 solution, and it uplifts on the round sphere to ADS5 cross S5, which is the near Eisen geometry of this brane. The second reason why these truncations are very powerful is because if you're interested in the dual field theory living on the boundary of the ADS space, and you only want to learn certain things about the lowest BPS multiplet, then you can actually compute them holographically only using the lower dimensional theory. You don't need to do the full computation in higher dimension. Okay, so there is such a consistent truncation around the near Eisen geometry of the D3 brane, and it turns out actually that over the time people have constructed consistent truncation around the near Eisen geometry of all the DP branes until P is equal to 0. So the natural question is to ask, okay, there's really a lot of text missing here. Okay. but the equation is here. So the natural question is to ask whether you can actually build a consistent truncation around the near-horizon geometry of the D-1 brane. And okay, to remind you, so the D-1 brane is a half supersymmetric solution of Euclidean type 2b supergravity. And it takes the following form. So the weird thing now is that the metric, I wrote it at ADS1 cross S9 earlier, but this is too naive. The metric in the Einstein frame is just flat Euclidean space. And here I wrote it in spherical coordinates. So this T here, which is some kind of Euclidean time, is really just a radius. And it has also a dilaton and an axion which are turned on, which is equal to some harmonic function, depending on the charge of the D-1 brane, which is related to n, the number of D brane. So this is the background for the D-1 brane, and so it was conjectured to be the holographic dual of the IKKT matrix model, and now the holographic coordinate is this radius or Euclidean time coordinate T. The question I ask now is whether it's possible to build a consistent truncation around this 9 sphere that you have here. And while there is absolutely no reason to expect based on symmetry argument that it exists, well, we still were able to construct it. So, I mean, this is the slide that essentially shows it. So the starting point is we take a subsector of Euclidean type 2b supergravity where you only have well, this is the Lagrangian, you just have the Ricci scalar, and then you have the dilaton and the axion. The fact that you have now switched to Euclidean signature flips the sign of the axion kinetic term, and this is what allows to a flat space solution, because the, the energy momentum tensor between the axion and the dilaton can actually vanish. And so the claim now is that if you do this truncation ansatz, where on the left-hand side you see the 10-dimensional fields, and on the right-hand side you see the fields of a one-dimensional theory, which is this one, where all the fields here only depend on this time coordinate t. And this mu here are the embedding coordinates of the sphere. So if you plug this truncation ansatz into the field equation of the theory, you will find actually the field equations of this lower dimensional theory. So let me describe a tiny bit what we have here. So the modes that you keep here are actually just scalar fields and some SO10 gauge fields. So you have a dilaton phi here. The dot is a derivative with respect to time. You have scalars that I call here Tij, which is a unimodular matrix. The scalars actually parameterize the Coset space, which is a cell 10 over SO10. So this is the kinetic term for these scalar fields. And this is the scalar potential for the scalar fields, which depend on the dilaton and this Ti and the scalars packaged inside the matrices Tij, which are symmetric and unimodular. And you also have an Einbein E. So of course here, I mean, it's a bit naive to precise this, but there are no curvature tensor. You're in one dimension, so that's why you don't see any Ricci scalar. That's also why you don't see any curvature for the SO10 gauge fields. So the only place where they appear are inside these covariant derivatives dt here. Yeah. So the variation with respect to this Einbein and these gauges, they actually just lead to first order constraint on this system. So you can call it supergravity in the sense that, I mean, it describes fluctuations, the lowest fluctuations of a gravitational theory in 10 dimensions. But if you look at it just from the point of view of one dimension, it's more, I mean, some SO10 gauge quantum mechanics. Okay. So yeah, the details, I mean, of course, are not so important of these big formulas. Now, the question is, you can say, okay, you have a consistent truncation, so you can look for solutions of this theory. The first thing you can look for is a solution which would preserve the SO10 invariance of the theory. So the only thing you can write down is actually the solution where this matrix Tij is just the identity. You set all the scalar fields to 0. And if you actually, I mean, and the Einbein takes a certain form, the dilaton as well. And if you plug this solution inside this truncation ansatz, you can uplift it to a solution in 10 dimensions. And what you find exactly is this solution again. So it contains the near-horizon geometry of the D-1 brane. Okay. So, of course, that's not the full story. I mean, in practice, you would like to say that you have a consistent truncation of the full type 2b theory, which also includes the p-forms and so on. But I mean, the truncation ansatz, although I think it will exist, will look extremely complicated. So instead of this, to really connect with the IKKT model, what we've decided to do is to actually directly supersymmetrize in one dimension. So let me say a few words about this. Again, the details are not so important, but the the few points that you should take away is that if you want to ask for maximal supersymmetry in one dimension, you have to kind of enlarge your fields content. So in the scalar sector, on top of this Einbein, dilaton, the gauge fields, and the scalar fields that were in TIJ, you have 120 more scalar fields that are axionic scalar fields. And then, of course, you have all the fermions. So here, of course, you're in one dimension, so they don't really have any Lorentz structure, but they do transform under the SO10 symmetry of the theory, and they transform as 32 component spinor on the SO10. So you have a gravitini, which has 32 components, some spin 1/2, which I call lambda, which has also 32 components. You have a vector spinor, which I call Ka. And essentially, if you turn the crank, well, you can actually derive the full maximally supersymmetric completion of this one-dimensional theory. The first terms in blue here, they were already present on the previous slide. This is now a kinetic term from these additional axionic scalar fields, the 120 additional scalar fields. You have a scalar potential, which is quite complicated. It contains the terms you saw on the previous slide, but now it also contains many other terms with the additional axionic scalar fields. It goes up to axions to the 10. You have a topological term which is quartic in this axionic scalar fields, and then you have all the fermionic terms, and you can notice here that you don't have any kinetic term for the gravitino because the Arita-Schwinger term in one dimension naturally vanishes. Okay, very good. So, of course, if I give you a supersymmetric Lagrangian, I should also give you the supersymmetric transformation, but there is no need to really dive into details here. But essentially, I just give you like the variations of the fermionic fields in the sector where these axionic fields Aijk is equal to 0. And what you see is that they take a rather simple form. And they involve this chirality, this SO10 chirality matrix gamma star. And what you can do is use them to find actually supersymmetric solution of this one-dimensional theory on top of the one that I already presented by finding configurations, bosonic configurations, which satisfies delta epsilon, I mean, variation of the supersymmetry variation of the fermion is equal to 0. Because in all this variation, one term carries the chirality matrix and the other one doesn't. What you can see very quickly here is that essentially you have only two possibilities. You can either have non-supersymmetric configurations or you can have half supersymmetric configurations. And in order to have these half supersymmetric configurations, the only possibility is that these variations have to recombine such that you get projectors on this supersymmetry parameter. And such that you're actually able to find, a killing spinor with only half of the components. And so in order to have these projectors that appear here, this imposes certain first-order equations on the bosonic fields. And you can check that these first-order equations on the bosonic fields, they actually imply all the field equations in the theory. And you can solve them also exactly. So this means that in this sector, where this axionic field Aijk is equal to 0, you're able to find the most general half supersymmetric solution of the theory. It takes the following form. So essentially, without loss of generality, you can write this Tij metric as being diagonal with some element on its diagonal, which are given by the following function in terms of the time t. So these Ci's are real constants that specify your solution. So you see that for Ci's that are not equal to each other, this solution typically break the SO10 symmetry. If you take all the Ci's to be equal, you recover the D-1 brane solution that I presented before. So this solution, when you actually break SO10, we expect them to correspond in the matrix model we expect them to be dual to states that are in the Coulomb range of the matrix model. We'll start turning on certain VEV for some of the operators that I will present before. So I wanted to say maybe one or two words about this solution, but I'm not sure I have time. So I'll just say that in the bulk, what they correspond to, when you uplift them, what you find is that actually the 10-dimensional metric is always flat, and it corresponds to actually taking the instanton, which were at t is equal to 0 before, and just smearing them in the 10-dimensional space in a way that preserve the symmetry that, like SOP times SOQ. So things I wanted to say here. So this is in some sense very analogous to the smear discrete brain of Friedman, Gupser, Pilch, and Warner for n equal 4 super young maths. Maybe one last thing, not to say too much thing on this slide, but these solutions you can actually uplift them even further to some solutions of pure Lorentzian gravity in 12 dimensions, and they actually correspond to PP wave solutions. This follows the work of Zeitlin in 97. Okay, so finally, in the last few minutes, let me come back to the matrix model. So this is the action I presented in the beginning. So X and psi were the bosonic and fermionic matrices. So you have 16 supercharges, because this time the spinor satisfies this Chiari condition, the supersymmetry parameter. And the algebra here, because you're in 0 dimension, there is no translation on the right-hand side of a commutator of 2 supersymmetry variation. It's just equal to an SUN rotation. Yeah. So the operators I'm interested in are the single trace operators. So the ones that take the following form with any number of X of bosonic and fermionic matrices inside the trace. And so the operators, those operators, if you factorize out the field equation of the theory, they arrive into certain supermultiplets. And among these supermultiplets, you either have long or short multiplets. The short multiplets, which are also known as BPS multiplets, they arrange into a tower, which I call Bn. And for each of these multiplets, for each n, it combines the following SO10 representation for the states. So it's always based on the lowest weight state, which corresponds to an operator where you take the trace of n bosonic matrices and you symmetrize and remove the trace. So if you look at the lowest one for n is equal to 2, what you find is the following representations for the operators that are inside of here. So 54 plus 144 and 120. The first one and the last one are bosonic operators. The last one is a fermionic one. And so the dictionary we proposed, these are the operators written in terms of the X and psi matrices. So as I said, this is bosonic operator, fermionic, and bosonic one. And so the dictionary that is purely based on kinematics at this point is between this lowest multiplex of BPS operators and the fields that appear in this one-dimensional supergravity, which I've shown you a few slides ago. So these are the scalar fields. This is this vector spinor that I showed you, and these are the axionic fields, 120 of them. And finally, yeah, you can also see, you can compute actually the supersymmetry variation of this multiplet of BPS operator. This is what you'll find. So there is some kind of important structure. So if you apply 2 supersymmetry transformation, you find 0. And this is due to the fact that since you don't have any translation in 0 dimension, I mean, this nilpotent structure emerges. And you can also see from here then that if you, for instance, turn on a VEV for this first operator, the one in the 54, theta AB, of course, you don't break any supersymmetry because it never appears on the right-hand side of the supersymmetry variations. Okay, so maybe I'll just give some future directions and then I'll stop. With this setup that we have now, of course, what would be nice to do is to have some clear computation of holographic correlators using the SO10 one-dimensional supergravity we constructed and to compare to certain correlation functions in IKKT matrix model. So this will require using the framework of holographic renormalization. But I should say here just that, I mean, this will be subtle, interesting but subtle, because these correlation functions that you're computing are really just numbers here, since you're in 0 dimension. So the normalization of this correlation function will be a subtle point. The other thing we could do is generalize this one-dimensional supergravity to SOPQ gauging, where P plus Q is equal to 10, so this should be quite easy to do. And these are usually expected to arise from Kaluza-Klein truncations on hyperboloids, starting from 10 dimensions. Another direction would be to look at truncation of this type 2b star supergravities in 10 dimensions of Chris Hull. I think this could have some importance if you want to actually now look at holography for the Lorentzian version of the IKKT model. And then finally, no, not finally, one of the things also you can do is look for other solutions in the SO10 gauge supergravity, and ones which involves axionic fields which do not vanish, and typically those are ones which are dual to mass deformations of the matrix model. So it'd be interesting to see whether we would be able to find a solution perhaps that is related to the mass deformation as polarized, that is known as polarized IKKT, or the solutions that are known as spherical branes. And then finally, but this is extremely speculative, but okay, I mean, it's a bit of a wishful thinking. I think this one-dimensional supergravity seems like an appropriate framework to use supersymmetric localization and obtain perhaps certain exact rhythms. And I'd be very curious to do a one-loop determinant computation using this one-dimensional theory and to see whether it reproduces maybe certain features of the results of Moore, Nekrasov, and Chatashvili, which have applied supersymmetric localization for IKKT and derived the partition function exactly. Thank you very much. Yeah.
So it looks like that small a's are responsible for these three-form fluxes in 10 dimensions. But is there any operator or these fields in 1 dimension that corresponds to the 5-form?
Sorry, the small a's, now they are fields actually in 1 dimension. These fields here.
Yeah.
Yeah.
It feels like they are sort of these modes of the 10-dimensional 3-form.
Yeah, so actually, yeah, because the full truncation, that is very nonlinear, they will actually spread in all of the fields in 10 dimension when you turn them on. So for sure, if you turn them off, you will not get any higher form in 10 dimension. They are the only contribution to this higher, for instance, the NSNS and RR 2 forms and the 4 form. Their truncation and that will definitely involve the scalar fields. So if you actually have solutions that have the scalar field set to 0, you will never uplift them to solutions where you have like RR and NSNS 2 forms turned on.
Right. So is it correct to say that they are sort of the one-dimensional analogs of these 3 forms? And I think I'm just still a bit confused. Are they the one-dimensional analogs of the 10-dimensional 3 forms? So if you take the 10-dimensional some component.
Well, I wouldn't say they are analogs, but for sure they will.
They come from those.
They will originate from those, yes. But
right. Is there anything that originates from the 5 forms? For example,
yeah, they will
have
also
all these matchings of operators with these modes, and there are these ones with commutators with 3 matrices, looks like the 3 form, but are there ones with 5 forms that?
Yeah, you can't draw such a direct dictionary. I mean, in order to have a solution with also a 4 form turned on, or the self-dual 4 form, for sure you will need a solution that also turns on this 120 scalars in 1 dimension. But yeah, the relation is very nonlinear. But yeah.
Thanks, Franz, for the interesting talk. In the next slide, where you present the solution, maybe it was the previous one.
This one?
No, where you find the solution of you're showing it. It's called sphere truncation or something like that. Yeah, yeah. What is the regime in which I should trust this solution in particular? What is the behavior of the string coupling as a function of this 1 dimension?
Well, so that's actually a very subtle point because here, I mean, so usually when you do this holography for DP branes where P is not -1, so you can trust the supergravity solution to do holography only in a certain range of the holographic radius, because you can interpret it as some energy. And so it shouldn't be too big, because otherwise the space would be too curved, or it should be too small, otherwise the dilaton would blow up. The problem is here that the near horizon geometry of this D-1 brane solution is actually flat.
And what about the asymptotics?
Sorry?
What about the asymptotic region?
The asymptotic is just flat space.
So you have flat space both in the asymptotic and the near horizon, is that what you said?
Yeah, yeah. So in the Einstein frame, this is completely flat. In the string frame, it becomes a wormhole which connects 2 asymptotic flick-like regions. But once you take the near horizon geometry, the near horizon is flat. Yeah.
Thanks.
So what is, I just missed, why you consider New Horizon limit at all? Your construction works for any,
Sorry?
why you're considering New Horizon limit here? So your construction works in general, right?
I'm not saying, in this case, I'm not saying that taking the near horizon limit is necessary. It's a,
Okay, but you change supersymmetry, so that presumably changes, is that the case or not?
I change supersymmetry.
When you take near horizon limit, in other examples, we know that supersymmetry is enhanced.
Well,
Here it doesn't happen. I don't remember. I don't know.
no, so here I'm completely blind to this. I mean,
But you use supersymmetry to classify your whatever states comparing. Your IKKT model has maximal supersymmetry as far as CFT, well, not CFT, as long as this zero-dimensional theory is concerned. It's just reduction of n equal 4.
Yeah.
So it should be matching to whatever supersymmetry you have in your supergraph.
Yeah, so
it should be important that you actually drop one in the dilaton, but I don't quite get where.
So in fact, the only thing you capture in the consistent congregation is really the solution where you drop the one.
Oh, it's only that one.
It's only this one that you reproduce.
Okay.
Yeah.
Second question: what happens if you repeat the same for D0 brane?
Yeah. So that actually, I've worked on that as well in some other people. In this case, yeah, there's a slide I skipped, but I'm not sure there is any text on it. Yeah, there is. It's this one. I wanted to mention it. There is a similar story where things are a bit more under control because this time the near horizon geometry is not just flat space, but it's really some ADS2 cross S8, which is warped by dilaton because. So what happens is that you have a consistent truncation of 2A supergravity on S8 to a theory in 2 dimensions, which is known as SO9 gauge supergravity. And there at the center of the moduli space, you have a solution which is not an ADS point, but a domain wall, so ADS with a non-constant dilaton. And if you uplift it, it's the same story. You get the near horizon geometry of the D0 brane, which is this warped ADS2 cross S8. And there actually people used the lower dimensional theory to compute certain 2-point and 3-point functions and match certain correlators in the BFSS matrix model, which is the dual. Yeah.
So I don't find any coupling constant in your theory, either matrix side or in the gravity side. So it looks like it's a comparing free theory with free theory. Is it true?
Yeah, yeah. This issue of the coupling constant in IKKT is a bit subtle because, as you see, you don't have a kinetic term in the action. So, I mean, you're free to just redefine your matrices to absorb what you call G-Young bits. So, how to make sense of the coupling constant in IKKT is a bit unclear to me. The only thing I can say is that what I'm talking about is that very large n. But at the same time, the original conjecture of the IKKT is that at large n, you should be really describing free type 2B string in flat space. And in a way, from the point of view of supergravity, it's a little bit what you're seeing. I mean, you're seeing essentially type 2B supergravity on flat space. The question is how to make this more precise. So the only things I've been saying so far here are just purely relying on like matching representations. And I'm not making any statement about the regime or the dynamics or anything.